In this video, we're going to talk about arithmetic and geometric means. And when you see the word mean, you might think that that's just kind of a fancy word for average. So we have two numbers, okay? We have 10 and 90, and we're asked, give us the arithmetic mean, or the average, of those two numbers. So I think we know how to do this. We would just add the two numbers together, and then we would say, well, I also have to divide these two numbers. And if we want to get really fancy, we would say that the number of terms, n, is 2. So we divide by 2. 100 divided by 2 is equal to 50. And that would be our arithmetic mean. Now, if we're going to get the geometric mean, we started with 10. We would multiply by 90. And that would give us 900. When we'd count again, there's two terms. N is equal to 2. At this time, we wouldn't divide by 2. We would raise to the power of 1 over 2, or 1 over n, whatever n, the number of our terms were over here. And some of you might recognize that that is the same thing as saying the square root of 900, which is 30. So why is there a difference in values here between 30, the geometric mean, and 50, which is the arithmetic mean? Well, let's look at another set of numbers. Let's say we're given 50 and 50, and this is far more obvious. We've got the average of those. Again, n is equal to 2, because there's 2 terms in this series. And that is equal to 50. The geometric mean, we take 50 and we multiply it by 50, and that gives us 2,500. Again, n is equal to 2. There's 2 terms in the sequence. And we'll say we'll raise this to the power of 1 over n, or 1 over 2 in this case, because there's 2 terms. Well, that is going to equal to 50. So why is it that in this case we have 50 and it's equal to our arithmetic mean, but in this earlier case, our geometric mean looks very different than our arithmetic mean? Well, this is because there are different properties between arithmetic and geometric means. Arithmetic means show the central tendency. So let's say that I drew a graph of values and I told you, okay, I want you to draw a line that kind of describes the central tendency of where all these values are. You might draw something that looks like this. You might draw something that looks like this. And that would be a great description of the central tendency of those values. And this is our average, or our mean. Okay, so the geometric property is of proportional growth. It's not the central tendency, it's the proportional growth. This is harder to visualize, but maybe one of the better visualizations is how interest works in a bank. So let's say that I have a bank and you gave me $1,000, okay? You're interested in investing. And I'm feeling generous, so I give you 10% on your $1,000 that you give me. And I would give you, at the end of the year, $1,100. Let's say that I'm going to give you 10% on the next year as well. So I look at that $1,100 and I say 10% get on top of that is going to be $1,210. But let's look at a different scenario. Let's say we start with our $1,000. You give me that, and I'm not so generous this time. I'm only going to give you 5% on that $1,000. So that's going to equal $1,050. And on the second year, I felt a little bad. I only give you 5%, so I'm going to bump that up to 15. And you'd think, okay, great. Well, I've matched my other case where I had 10% and 10% growth. That's 20% growth. And down here we have 5% growth and 15% growth. So you'd think, oh, great, that'd be 1210 that I would expect. But you would be wrong. It would not be 1210. And that's because it's harder for this small balance to grow 15% and equal $1,210. In other words, you're penalized more for small proportions. So you're penalized more for small proportions then you are rewarded for the larger proportions. And that's important to keep in mind, that when there is volatility between the returns, you end up with less. And that's actually quite an important lesson. So the proportional growth is what's important here. It has to do with the starting amount at the beginning of a year, or at a specific interval. That needs to be consistent for you to maximize gains. You can't have volatility, have the same amount of growth over the years, and then expect the same outcome. So what do these equations look like? How do we actually write this down? Well, for arithmetic sequences, let's just pull up our early example of 10 and 90. We know that there are two terms in our sequence of 10 and 90, so we'll just write down here n is equal to 2. 10 and 90 divided by 2 is equal to 50. So let's look at this. How does this equal to this? Well, this first letter, this is x bar, and you might write it as x bar a, you don't always have to, but x bar is equal to 1 over n times whatever this thing is over here, 1 over n. So we know the value of n in our sequence of 10 and 90. N is equal to 2, right? So we can say x bar is equal to 1 over 2. That's our first term. And then this scary looking thing, this is sigma, the Greek letter sigma, and it's just basically saying the sum of a series. And it's more specifically the sum of a series x. X that has a count of I. I is just the number of terms in that sequence. So the sum of series x, and it's saying the start value, in other words, where should we start grabbing values within our sequence? Well, that's equal to 1. I is equal to 1. 1 is the start value, and the stop value is n. Well, what's n in our case? N is equal to 2. So we're going to start with the first term, and we're going to end at our last term, the number of our terms, n. So that means it's going to look like this. 10 plus, because we're getting the sum of these series, 10 plus 90, and it's all divided by 2. It's multiplied by 1 over 2. It's the same thing. I want you to see it's the same thing as we have up here. So that's arithmetic notation. That's arithmetic mean notation, and it is the same thing. Now, what about geometric means? Now we have our example, 10 times 90 is equal to, and then we raise this to the power of 1 over n, which is equal to 50. How is that similar to our notation up here? Again, we'll write x bar, and you don't have to write the g, but this is just to show that it's a geometric sequence. X bar is equal to, now we got a new funky letter here. What is this thing? This is capital pi, and this is a Greek letter for representing the product of a series. It's the same as before. We have our start value, in other words, knowing where to grab the first value from in our series, and our stop value, which is where do we end? Where do we stop grabbing values? So we start at our first value, 10. We stop at our last value, which is 90, because there's two values. We multiply the two together, because capital pi is telling us to multiply, find the product. And then we take all of that and we raise it to the power of 1 over n. And we know what the value of n is. N is 2. There are 2 terms in our sequence. So we raise it to the power of 1 over 2. And so that's how we describe our geometric means in terms of notation. When I first looked at arithmetic and geometric means, it was hard for me to figure out, well, what's the value here? I know that arithmetic means shows the central tendency, and geometric means are showing the proportion, but how can we use that and do cool stuff with it? So here's an example. If I have a picture of myself, and I was asked to create a program to blur the pixels in this image, I could use the power of an arithmetic mean. So I grab just a little grid of pixels from this image, 3 by 3 grid, and these are just some simple values. if I were to take these values and flatten them out, and I call that sequence xi, it'd be something like this. If I were to grab the sequence, it looks something like this. And now to blur that central pixel, I would be taking the average of that entire sequence. So I would be dividing this entire sequence by 9. So I would take the sum of the sequence, and then I would divide it by 9. And that would give me a blurred central pixel. I think that's pretty cool. Now, what would happen if we took the geometric mean of this grid? What would that give us? Well, that would give us a denoised version of the pixel. Because what it's doing is it's basically saying, let's take away the deviation of this series, and let's just return the factor of it. So returning the factor, keeping the proportion, but removing the deviation is the same thing as denoising. And that's pretty powerful, because now we can scale this concept through as big of a picture as we want. And we can just get a program, and of course computers run very fast. This can scale into massive, massive photos. So when you think of a blur effect on your phone or on your computer, that's all that it's doing. Usually it's just using this very, very simple algorithm called box blur. Or if you're wanting to denoise, remove noise, you can just take the geometric mean and then update that central pixel, and then go through the entire image, grab the next set of pixels, update it, and keep on updating as you're going throughout the image. So that's pretty cool. And I hope that you can see kind of the power of these very simple properties when you scale and apply computer power to them. So one last thing that I'm going to say is that arithmetic means and geometric means are limited in the type of input that they can have. So arithmetic means are, you need to have your numbers. So let's say we have a sequence xi, a sequence of numbers xi, that those need to be in, and we use, to denote in, we use the Greek letter epsilon. This just means in. We say our sequence of numbers needs to be in real numbers. So numbers like 1, 2, 3, 4, minus 1, minus 2. We can have an average of positive and negative numbers. But if we have a geometric sequence, those numbers need to be in a range that is greater than 0. We can't have it as 0, because if we were to take a sequence that looks something like this, as soon as we multiply it by 0, this entire sequence becomes equal to 0. And then that's no good. That doesn't actually communicate the factor of that sequence. So we cannot have it equal to 0. No number in this sequence can be equal to 0 if we're trying to get the geometric means. And sometimes in statistics, what you can do is you can add 1 to all the values, and or very small number, and that'll eliminate this problem of always becoming 0. But that is something to keep in mind. You cannot have 0. Sometimes that's called zero frequency. So we need to have numbers that are greater than 0.